This lesson is a redox review, and this lesson is in preparation for our unit on electrochemistry. So let's start out by reviewing the difference between oxidation state, or oxidation number, and formal charge. These two are related. So the difference is in how the bonding electrons are assigned. So in oxidation state, the bonding electrons are assigned to the more electronegative element. Of the two elements in the bond. Now, in formal charge, those bonding electrons are evenly divided between the bonding atoms. So here the bonding electrons are divided evenly between the two atoms, in the bond. So what we're doing is an oxidation state. We're treating every atom as if it is an ion, whereas in formal charge, we're treating every bond as if it is purely non-covalent. So if we have a polar covalent bond, neither of these is exactly describing the bonding in the electron in the bond, but we have uses for each of these. Formal charge, as we've seen, is useful for predicting structure. And oxidation state, this is essential for redox reactions and electrochemistry. So it does give us an idea of where the electron density is. For both of these, the value of the oxidation state, or the value of the formal charge, is equal to the number of the valence electrons in the elemental state, as if the atom was by itself, minus the number of assigned electrons. And this is how we assign them. So let's look, for example, at the difference between oxidation state and formal charge in methane. So in CH4, we've got carbon, 4 hydrogens around it, 8 valence electrons, 4 from the carbon, and 1 each from each hydrogen. So we're doing the oxidation state of the carbon. So that equals carbon's valence electrons when carbon is neutral, carbon in group 14, so that's 4, minus, now we have to assign these bonding electrons. They go to the more electronegative element, and carbon is slightly more electronegative than hydrogen. So we're going to give all of these electrons to the carbon. So we have 8 electrons assigned to it. So 4 minus 8, the oxidation state of carbon and methane is -4. The oxidation state of hydrogen, hydrogen has 1 valence electron. Here, it has no electrons assigned to it, so it has an oxidation state of +1. And there's 4 hydrogens, so they add up to +4, +4 and -4. We have a total of 0 for the sum of the oxidation states in the molecule. If we go over here to formal charge with the same thing, with methane, and we want the formal charge of carbon, so 4 valence electrons minus, now we divide the bonding electrons evenly. We don't care about electronegativity. So carbon will get 1. Okay, so carbon gets 4 electrons, so it has a formal charge of 0. The formal charge of the hydrogens, each hydrogen is 1 valence electron, and it gets 1, it has 1 assigned to it, -1 equals 0. So the formal charges in methane are 0, but the oxidation states -4 and +1. So this means that carbon has more electron density than for the hydrogen. Off the page there. Okay. But we don't always want to have to draw the Lewis structure and figure it out, especially when we have ionic compounds and polyatomic ions. So we have our oxidation state rules. All right, so the oxidation state of an element in its elemental state is 0. So that would mean if we had some pure sodium, Na, its oxidation state would be 0. If we have some oxygen gas, that's its elemental state, it's 0. So an element that is not in a compound has an oxidation state of 0, and it is neutral. Number 2, the oxidation state of monatomic ions equals the charge of the ions. So if we have sodium chloride, sodium is a +1 ion, it has an oxidation state of +1. Number 3, the sum of the oxidation states in a compound equals 0, and we just saw that with the methane. And 4, the sum of the oxidation states in a polyatomic ion equals the charge of the ion. 5, the oxidation state of fluorine in compounds is always -1, because fluorine is the most electronegative on the periodic table, so it's going to be assigned all of the bonding electrons. 6, the oxidation state of hydrogen in compounds is +1, except in metal hydrides when it is -1. So if we have HCl, hydrogen is +1, chlorine is -1, they add up to 0. But if we have NaH, this is sodium hydride, our sodium ion is +1, the hydride ion is -1. Another metal hydride, we could have calcium hydride, CaH2. Calcium is a 2+ or +2 oxidation state. Our hydrogen then is -1, 2 of them give a total of -2. So when hydrogen is paired with a metal, it is the anion, and it has a negative oxidation state. The oxidation state of oxygen in compounds, it's usually -2, but we have a few exceptions. When it is with fluorine, number 5 supersedes number 7. Fluorine is always going to be -1. So we have the compound OF2, oxygen difluoride. So fluorine is -1. There's 2 of them, so the total is a -2 charge. The compound has to equal 0. Oxygen is our X, so that means oxygen has to be +2 oxidation state. Fluorine being more electronegative pulls the electron density towards itself. So as you can imagine, this is a very reactive compound because oxygen likes to be in a -2 oxidation state. And another important exception, oh man, that whole thing was off the page. Sorry about that. Our next important exception is in peroxides, such as H2O2, hydrogen peroxide. So our hydrogen +1 for a total of +2. The whole thing has to equal 0. So our X equals -1. So this is where oxygen has a oxidation state of -1. Okay. All right, so we'll do some examples, a few examples of assigning oxidation states. So let's see, we'll look at carbon tetrachloride, CCl4. So it's a neutral compound, so the sum of our oxidation states has to equal 0. So we have chlorine. Chlorine monatomic ion is -1. So we get a total of -4, -1 times 4. And then our carbon is X. So X equals 4. So the carbon in this compound is +4, the oxidation state. All right, our next example, we'll do the dichromate ion, Cr2O7, with a 2- charge. So now the sum of our charges has to equal -2. Oxygen, it's not in those exception categories, so it will be -2. -2 times 7 is a -14. There are 2 chromiums. So we have our equation 2x minus 14 equals -2. So 2x equals +12. So x equals +6. So each chromium has an oxidation state of +6 in the dichromate ion. Now, if we have ammonium sulfate, so there is our neutral compound. So we could set all of the oxidation states equal to 0, or we can do each ion separately. So I'm just going to do it that way. So I'm going to do the NH4 plus ion. So the sum of those charges have to equal 1. Hydrogen, it's not a hydride, so it's going to be a +1. +1 times 4 is +4. Our nitrogen then is X, so X equals -3. So the oxidation state of nitrogen is -3, and that of hydrogen is +1. It doesn't matter that there's 2 of them. Each ammonium ion has the same oxidation state for its elements. So then we have SO4 with a 2- charge. So the sum of the oxidation states must equal -2. Oxygen, that's not an exception there, so oxygen is going to be -2 times 4, -8, 1 sulfur, X. So our X equals +6. So sulfur is +6 and oxygen is -2. Now we're going to move on to redox reactions. Now, for redox reactions, we can use our little mnemonic. Leo says, grr. To have a redox reaction, we must have oxidation. And Leo stands for lose electrons. Then you have oxidation. And grr stands for gain electrons reduction. So for a redox reaction, you must have one substance that loses electrons, and you must have one substance that gains electrons. And to figure it out, it's often helpful just to think of it like a number line. So if you have a substance and it can start anywhere, but if it goes up the number line, and it can go from -3 to -2 or -1 to +3, as long as it goes up the number line, then it is oxidation. Because when you get more positive, it's because you've lost negative electrons. And no matter where you start, if you go down, then it is reduction. So we have to go up and down. But to have a redox reaction, you must have a change in oxidation states. Otherwise, you do not have a redox reaction. So let's look at some examples here. So we're going to look at this. This is the decomposition of calcium hydroxide into calcium oxide and water. So metal hydroxides decompose into metal oxides and water. And we want to know, is this a redox reaction? So we need to figure out what is the oxidation state of each element. So in hydroxide, this is the calcium ion, 2 plus ion, so we have a +2 oxidation state. And then hydroxide, I'll just do this, OH minus, it has to equal -1. Oxygen is going to be -2. So that means hydrogen has to be a +1. So oxygen is -2, hydrogen is +1. In calcium oxide, calcium ion is +2. The oxide ion is -2. In water, oxygen gets the -2. So each hydrogen has to be a +1. So the calcium stays the same, oxygen stays the same, hydrogen stays the same. So this is not redox. We do not have a change in oxidation state. Okay, for our next example, let's look at the good old Bunsen burner reaction. So we have CH4, methane gas, plus oxygen gas, goes to carbon dioxide gas, and water. So here we want to do our oxidation states. So we know that hydrogen, when it's with a non-metal, will be a +1 for a total of +4. So our carbon has to be a -4 oxidation state. O2, that's oxygen in its elemental form, so it has an oxidation state of 0. In carbon dioxide, the oxygen gets a -2. The total then is -4. The whole thing has to equal 0. So our carbon is going to have to be a +4. And in water, we already did that up there. The hydrogen's +1. The oxygen is -2. So now, the carbon and methane goes from -4 to +4. It's going up the number line. That's oxidation. The oxygen is going from 0 to -2. It's going down the number line. That is reduction. So yes, this is a redox. And all combustion reactions actually are redox reaction. So since the carbon is going up the number line, it's being oxidized. We say that the whole thing, so we say that the CH4 gets oxidized, and then the oxygen, the O2, gets reduced. And then for our agents, we just flip it. So the substance that gets oxidized reduces something else. So this is the reducing agent. And then the substance that gets reduced is the oxidizing agent. So I just figure out what gets oxidized, what gets reduced, and then I know that I have to flip it to get the agent. All right, so you must have a change in oxidation state for a redox reaction. And now we're going to go on to balancing redox reaction. And there's different methods. There's the oxidation number method, but for electrochemistry, we want to use the half reaction method. That's going to be really important, and you'll see why when we do electrochemistry. Okay, so this is our equation. So aluminum solid, Cu2 plus aqueous yields Al3 plus aqueous and Cu solid. So of course this copper would have to be copper sulfate or copper chloride. We have a spectator ion that canceled out. Maybe it's nitrate, but this is our net ionic equation. All right, so first we're going to do our oxidation half reaction. Oops, that looks like a Q. Oxidation half reaction. Okay, so we have to figure out what's being oxidized. Well, aluminum, this is in its elemental state, is 0. Copper in its elemental state is 0. So the aluminum is going from 0 to +3. It is going up the number line. It is being oxidized. So our half reaction, we take aluminum, goes to Al3 plus and 3 electrons, because that's how many electrons the aluminum lost to become the Al3 plus ion. So if we added these together, we would get back to neutral aluminum. All right, and then we want to do our reduction half reaction. Okay, so the copper is going from +2 to 0. It's going down the number line. It is being reduced. The Cu2 plus, in order to become Cu, has to gain 2 electrons. So when we have the oxidation half reaction, the electrons will always be on the product side. And for the reduction half reactions, the electrons will always be on the reactant side. Now, we want to be able to add these up, and we need to cross out the electrons. So I need to multiply all my coefficients by 2, and then multiply all these by 3. Okay, so we're going to multiply this by 2. So we get 2, 2, and 2 times 3 gives us 6 electrons. And now this we're going to multiply by 3. So we get 3, 6, and 3. So now I add my 2 reactions. I have 6 electrons on both sides, so they cancel out. And my full equation then is 2Al plus 3 Cu2 plus goes to 2Al3 plus 3 Cu. And you always want to check for both atom balance and charge balance. 2 aluminum, 2 aluminum, 3 copper, 3 copper. 3 times 2, I have a +6 on this side, that's 0. 2 times 3, I have a +6, that's 0. So I have my charge balance as well as the atom balance. Okay, let's do one that's a little trickier. The following reaction takes place in acidic solution, balanced by the half reaction method. Okay, so this is important, acidic solution. That means that we have water molecules and we have H+. So maybe we have some hydrochloric acid or some sulfuric acid. Something has put H+ into our solution. Okay, so I always like to start out with the oxidation half reaction first. We need to get some oxidation numbers here. The rest are ions. So for MnO4 minus, the sum of the oxidation numbers has to equal -1. Oxygen will be a -2. 2 times 4 is -8. So that means that our manganese is going to have to be a +7 to give us a -1. Okay, so now we can see that iron goes up the number line, it's being oxidized, and the manganese is going down the number line, it's gaining electrons and being reduced. So for our oxidation half reaction, we have the Fe2 plus going to Fe3 plus 1 electron. It loses 1 electron. Then for our reduction half reaction, we have to take the whole species. So we have the MnO4 minus. To go from +7 to +2, it has to gain 5 electrons. And then it goes to Mn2 plus. Okay, we're not finished here yet. We have 4 oxygens here. We have to have 4 oxygens over there. Where are we going to get 4 oxygens? From the water. We're in acidic solution. So we put in 4H2O. So that's good for the oxygen, but now we've introduced 8 hydrogens. So we need 8 hydrogens over here. Where are we going to get it? From our acidic solution. So we can put in 8H plus on that side. So now we have our atom balance. So we want to add up our reactions, and we have to have the same number of electrons so that we can cancel them out. So we need 5 electrons, so we have to multiply all of our coefficients by 5. So we have 5, 5, and change that to a 5. Now the 5 electrons cancel out, and we can write our final equation. So 8H plus 5 Fe2 plus MnO4 minus yields Fe3 plus Mn2 plus 4H2O. And then we want to check our atom balance and our charge balance. 8 hydrogens, 5 irons, 1 Mn, 4 O's, 4 O's. Great. Now we check our charge balance. So here we have 8H pluses, so that's plus 8. 5 times 2, that's plus 10. Minus 1 gives us a total of plus 17 on this side. On this side, we have plus 3, and then we have plus 2. I need a 5 here. I was like, what the heck? That wasn't working out. Okay, 5 times 3 is 15. So plus 15 plus 2 equals plus 17. So I have my charge balance as well as the atom balance. And then remember that we can do titrations with redox reactions. So we'll use that previous reaction and look at this problem. 17.38 milliliters of 0.1500 molar potassium permanganate was used to titrate 20.00 milliliters of iron Roman numeral 2 chloride to the end point. What is the molarity of the FeCl2? So I've done a little drawing of our titration setup. So we have an Erlenmeyer flask with our solution of FeCl2. And then in the burette, we've got our potassium permanganate. So this MnO4 minus comes from the potassium permanganate, and the Fe2 plus comes from the FeCl2. So the potassium ion and the chloride ions are spectator ions, and they do not show up in the net ionic equation. All right, so to do this, we can just do this basically using stoichiometry. So we have the volume and the molarity of the potassium permanganate. So we can figure out the moles of the permanganate and then just use stoichiometry to get the moles of the iron and then change that to molarity. All right, so first I'm going to figure out how many moles of MnO4 minus I have. So X moles, MnO4 minus, set that equal to our volume, and I'm going to change that to liters, 0.01738 liters, times our molarity, 0.1500 moles of KMNO4 for every 1 liter, times 1 mole of MnO4 minus for every 1 mole of KMNO4. Liters cancels liters, moles of potassium permanganate cancel potassium permanganate, and I'm left with moles of permanganate ion. So let's calculate that out. So we have 0.1738 times 0.15 equals. So we get 0.02607 moles of MnO4 minus. I'm just going to put this up here. 0.02607 moles. And I need to find the moles of the iron Roman numeral 2 ions, and then I can figure out the molarity. So this is just a simple mole ratio. So X moles of Fe2 plus equals 0.2607 moles of MnO4 minus times, from my coefficients, 5 moles of Fe2 plus for every 1 mole of MnO4 minus. Okay, so multiply that by 5. So we get 0.13035. I'll just keep that extra 5. Even though with sig figs, it should be 4 sig figs. Okay, I'll do the 4 sig figs at the end. So now we just need to figure out our molarity. So this number of moles of Fe2 plus is in that 20 milliliters. The moles are our original moles. So X moles per liter of the Fe2 plus equals 0.13035 moles of Fe2 plus divided by, change those milliliters to liters, so 20 milliliters is 0.02000 liters. So do the math, divided by 0.02 equals, I think I did something wrong. Oh, that's supposed to have a 0 there, I bet. No, what's wrong? 0.13035 divided by 0.02 equals, oh, that's saying 6.5. I don't think it's 6.5. I did something wrong somewhere. I don't know where. Could that be right? Oh, I don't know. I guess I'll just put it. I don't think that's right. 6.518 molar Fe2 plus. I do not think that's right. Let me do my calculations again. 0.01738 times 0.15 equals. Oh, that's where it is. This is 0.0. 2 zeros there. So that gets a 0 there, and that's a 0 there. And this is 0.6518 molar Fe2 plus. All right. So be careful with your digits. There's our correct answer. All right, so next we will jump into electrochemistry.